In my own experience in consulting and advising health and fitness practitioners who work largely with the obese and overweight population, I have often noticed a lack of basic literacy in the mechanisms underlying weight loss or fat loss. When most people refer to fat, they are referring to adipose tissue. Adipose is often called fat because it is where fat, a fuel molecule, is largely stored in the body, as I emphasized at the beginning of this lecture series. Now, the total mass of intracellular fat molecules like triglycerides largely contributes to the mass and size of the adipose cells or adipocytes, which in turn contributes to the size and mass of the adipose tissue. Thus, weight/fat loss starts by getting rid of the mass of these fat molecules in order to shrink the adipocytes, which in turn would reduce adipose tissue mass. So where do the fat molecules go during situations of weight or fat loss? Now, in a survey of 150 health and fitness professionals, which comprised of family physicians, dietitians, and personal trainers, they were asked the question, when somebody loses weight, where does the fat go? And a majority of these professionals who deal with obesity or overweight individuals said that it turns into energy. This is incorrect based on the laws of thermodynamics, which states that energy can't be destroyed or created, meaning fat cannot turn into energy. That is physically impossible and against physical laws. The fat molecule is fuel, and like any fuel, it is a source of energy. The energy is released, not created, it is released from the fuel molecule in the form of heat or in a form that can be transferred and temporarily stored in an energy compound called ATP. This occurs when the fat molecule is oxidized, which most refer to as simply burning of the fuel. Now, some of these professionals said fat turns into feces. So when you lose fat, the fat exits your body in the form of feces. This is untrue. Feces are generally stuff from food that was not absorbed. So fat does not turn into feces during situations of weight loss. Some professionals said that fat turns into muscle. I'm not going to go into this in much more detail because I trust that my students are smart enough to understand that adipose tissue just does not convert itself to a whole nother type of tissue, in this case, muscle. Now, the answer that only 3 out of 150 professionals gave was CO2 and H2O, carbon dioxide and water, respectively. This is the correct answer, with sweat and urine being partly correct, and you'll understand why in a second. Now, the mass of a fat molecule is made up of carbons, hydrogens, and oxygens, each of which has its own mass according to the periodic table of elements. When the fat molecule is oxidized to release its energy to form heat or ATP, the mass of the carbons, hydrogens, and oxygens of that fuel molecule is conserved. It does not simply disappear from existence. That would be called magic, which doesn't exist. Mass is always conserved. It just takes different forms. In the case for fat and other fuel molecules as well, like carbohydrates, the carbons, hydrogens, and oxygens are just converted to other molecules. In this case, CO2 and H2O, the only 2 molecules that can be expelled or exhausted from the body. Therefore, the mass of fat molecules are eventually exhaled, urinated, and or sweated out of the body. This is why I said sweat and urine is partly correct. Now, when this mass that is exhausted from the body or expelled from the body in the form of CO2 and H2O is not replenished through the mass of fuel molecules or nutrients that we consume and absorb, then body weight or mass reduction will occur. There's less fuel mass coming in than fuel mass going out in the form of CO2 and H2O. Now, this concept is as simple as imagining a container full of sand. The mass of the container is comprised of the materials of the container, but also the mass of the sand inside the container. Now, to reduce the mass of the container, what would you do? You would take mass out of the container by removing some sand out of it. By doing so, the mass of the container will decrease even if you took a gram of sand out of the container. This is the same idea when it comes to fat loss. The container is the adipose cell. The sand is the fat molecules stored inside the adipose cells. When you want to reduce the mass of the container, you would simply take sand out of the container. In the same way, to reduce the mass of the adipose cells, you must remove the fat inside it. How do you do that? The fat molecules must be oxidized or broken apart. It must be used for energy. And in so doing, the carbons, hydrogens, and oxygens that make up the fat molecule must be converted to something that can be exhausted, CO2 and H2O, which is eventually removed from the adipose cell and from the body. Thus, the adipose cell or the container loses mass. Let me give you another analogy. Say you have a container full of wood chips. The mass of the container is largely determined by the total mass of the wood chips inside of it. Say you put the wood chips on fire and let it all burn out. Would you say the mass of the container decreases? Yes, it would get lighter, if you will. How? You would say it's because there are no more wood chips in the container. Well, where did that wood go? Did it simply disappear? No. The wood was burned. In other words, the wood molecules underwent chemical reactions to release energy in the form of heat and light in this case, and through that process, the mass of the wood chip molecules were conserved and converted into another molecule, mainly carbon monoxide. The carbon monoxide then leaves the container as gas. The mass of the wood chip molecules were conserved in the form of carbon monoxide. It did not just disappear. In this example, the mass of the wood chips in the container decreased, and thus the mass of the overall container was reduced. I want you now to relate this example to fat loss and the reduction of the adipose cell mass and size. Now, another way that I like to explain the basics of fat loss is by relating it to an automobile. Now, by the end of this section, you will understand the basics of weight stabilization, weight gain, and weight loss, and you will see that weight control is very simple in concept and does not need to be overcomplicated like most of society likes to do. Now, let's start with describing this automobile. This automobile has a given mass, and as indicated in box number 1, there is a certain mass of fuel inside the fuel tank, which contributes to the overall mass of the car. The mass of the fuel is determined by the mass of the fuel molecules. The mass of the fuel molecules is determined by the total mass of carbons and hydrogens that make up the fuel molecules. Now, as the engine runs, the fuel can be mobilized through hoses to the engine. And in the engine, combustion, or quote-unquote burning of the fuel occurs. This is another way of saying the fuel is being oxidized. During this process, just like fuel in the body, the fuel molecules are broken apart or catabolized. And in so doing, energy within the fuel molecules are being released. The energy, just like in the human body, is released in the form of heat and also used to run the engine. This is why your car engine not only runs when fuel is being utilized, but heat is also generated. Your car warms up. So then what happens to the fuel molecules as it's being oxidized in the engine to run the car? Do they disappear? Well, according to the law of conservation of mass, this cannot happen, since things with mass like the fuel molecules cannot just disappear. Carbons and hydrogens that make up the fuel molecules cannot just simply disappear off the face of the planet. They are conserved, but in a different molecular form. In this case, the carbons and hydrogens that make up the mass of the fuel molecules are converted to other molecules like CO2 and carbon monoxide with the help of oxygen from the air. And these new molecules can be exhausted from the car, out the tailpipe. So when the fuel depletes in the car's fuel tank as it runs, where does the fuel go? It goes out the tailpipe in the form of carbon monoxide or carbon dioxide gas. And thus, as the car runs and utilizes the fuel, and as the fuel mass is exhausted out of the tailpipe after it is oxidized in the engine, the mass of the car decreases. So let's relate this process to the human body. Now think of this fuel tank in this car as adipose cells, which make up our adipose tissue. Now the fuel that is stored in adipose cells is mainly fat and a bit of carbohydrates as well. And these fuel molecules are made up of carbons, hydrogens, and oxygens, which in total contribute to the mass of the fuel that is stored inside the adipose cell. And this in turn contributes to the mass of the adipose cell, and that in turn contributes to the mass of the adipose tissue, which in turn contributes to the mass of the entire body. Now, the fuel in adipose cells can be mobilized to other cells, just like the fuel in the car. Within the cell, the fuel is needed to run the cell, just like how fuel of a car is needed to run the engine. Now, in the cell, the fuel is oxidized or broken apart to release energy that is needed for cellular processes and to also form heat. That's called thermogenesis, just like how the car's engine utilizes fuel. The carbons, hydrogens, and oxygens that make up the mass of the fuel molecules are converted to other molecules with the help of oxygen from the air that we breathe in. Again, remember the law of conservation of mass. The fuel molecule, like fat, does not simply disappear. The mass of the fuel molecule, which is made up of the mass of carbons, hydrogens, and oxygens, is conserved, but in a different molecular form: carbon dioxide and H2O, the two known products of fuel metabolism or oxidation in the human body. These new molecules can be exhausted from the body through ventilation, meaning expiratory gases, sweat, and urine. And thus the mass of the fuel molecules, which again makes up the mass of the adipose cell, which makes up the mass of the adipose tissue, which contributes to the mass of the body, is thereby reduced. You can see now that this dynamic is similar to that of a car. So going back to the survey question, where does the fat go when we lose weight? You breathe out, you sweat out, and you urinate the mass of the fat molecules in an exhaustible form, CO2 and or H2O. So let's imagine this, going back to the automobile analogy. Say you had a full tank of gas or fuel, and someone was filling up the tank while the engine was running and replacing the mass of the fuel that was depleted with new fuel. In other words, the mass of new fuel coming into the tank equals the mass of the fuel that is exhausted out the tailpipe in the form of carbon dioxide, carbon monoxide, and also water vapor. Since fuel is the source of energy, and fuel and energy go hand in hand, you can think of this as the energy in the new fuel molecules coming into the tank equals the energy that is expended by the car. You can see I am alluding to the classic energy balance model here. So with this situation here, the mass of the fuel inside the car, and therefore the mass of the tank, and therefore the mass of the car, would not change no matter how much time has passed. This reflects a situation in which there is a balance between the mass coming in and the mass going out of the tailpipe. We can view this also as a balance between the energy coming in and the energy being expended by the car. In other words, an energy balance. There is no energy deficit or an energy surplus. Relating this to mass, there is no fuel mass deficit or fuel mass surplus. Mass intake is equal to mass exiting the car. Now consider this analogy in the context of human body mass control. Would this example represent body mass loss, gain, or stabilization? As you might have likely guessed, it represents body mass or weight stabilization because there is an equal exchange of mass coming in from exogenous fuel or nutrients from food and fuel mass going out of the body in the form of CO2 and H2O after the fuel is oxidized within various cells in the body. Simply put, the fuel mass coming into the body is replacing, or in more technical terms, replenishing the fuel that was oxidized and eventually expelled from the body in the form of CO2 and H2O. Now, moving forward, what if the fuel tank is hypothetically ever expanding like a balloon, and each day someone filled the tank up with more fuel and thus fuel mass than the fuel mass exhausted from the tailpipe, meaning the mass of new fuel is greater than the mass of the fuel that was oxidized in the engine and exhausted from the car in the form of CO2 and CO. You can think of this as the energy in the new fuel molecule coming into the car being greater than the energy that is expended by the car. In this situation, we know that the mass of the fuel in the car, therefore the mass of the tank, and therefore the mass of the car would increase over time since more mass is coming in than going out. There is a positive balance, or shall I say imbalance, between the mass or energy coming in versus going out. This can be viewed as a fuel mass surplus or energy surplus, meaning more than what the car needs. But the tank, since it is expandable, is able to hold onto this surplus of fuel. But in so doing, the mass of the car will increase. So consider this analogy in the context of human body mass control. We can clearly see that this represents body mass gain. Now, I know this car example seems simplistic, but this is really the basics of body mass control. There is interestingly many parallels to human metabolism and machines that utilize fuel. So to summarize, this analogy represents weight gain situations because there is more mass coming in from exogenous fuel or nutrients than fuel mass exhausted as CO2 and H2O after it is oxidized for energy. Just like the car example, there is a fuel and thus energy surplus, and because adipose is essentially a very expandable fuel tank in the human body, and because biological organisms love to hold on to extra fuel to ensure survival, our body will hold on to this surplus. So over time, with this situation of overfueling, the fuel mass inside the body will increase, and thus increasing the mass and size of the fuel tank, which is the adipose cell, which in turn will increase the adipose tissue mass, which in turn will increase whole body mass. Now let's go back to this car analogy one last time. Now in this situation, each day someone is only filling the tank up with half the fuel that was utilized and exhausted, meaning the mass of the fuel coming in is less than the mass of the fuel going out in the form of CO2 and CO. Again, think of this as the energy in the new fuel molecules coming in being less than the energy that is expended by the car. With that, the mass of the fuel in the car, and thus the mass of the tank, and thus the mass of the car, would decrease over time since more mass is going out than coming in. This is representative of an energy deficit or a negative energy balance, or in other words, a negative fuel mass balance. Now think about this for future discussion in this lecture. If this cycle continues, what happens to the fuel in the tank and what happens to the engine? Well, eventually the fuel will run out since the engine utilizes the same amount of fuel and thus expends the same amount of energy every day to keep it running. But only half of that fuel is replaced. So eventually the tank will be fully depleted and the engine will stop running. You could say that the car would die. What if this happened to the human body? What if you put less fuel and thus energy into the body than what is being used and expended? You know you will lose weight, but does your engine stop eventually because fuel runs out? No, right? The body keeps running somehow. How is this possible? Well, perhaps the body adapts to the lesser fuel coming in. In other words, the engine, our body, learns to use less fuel and expend less energy. More on this later. This will be a very important piece of this lecture series. But for now, let's just relate this to body mass control. This example right here represents human body mass reduction, or simply weight loss. Now, there is less mass coming in from exogenous fuels than fuel mass going out in the form of CO2 and H2O after it is oxidized. In other words, the fuel mass coming in is not fully replacing the fuel that was oxidized and eventually expelled from the body in the form of CO2 and H2O. In time, the mass of the fuel inside the body will decrease and reduce the mass of the cells in which it was stored, like adipose cells, and thus reduce the mass of adipose tissue and eventually the whole body. So, as a bottom line regarding the fundamentals of body mass control, by the laws of this physical universe, alluding mainly to the law of conservation of mass, the only way to lose total body mass is to take the stuff that make up your mass out of your body, the container. This stuff are carbons, hydrogens, and oxygens, which make up the mass of your fuel molecules, like fat. Our body is the container, and the carbons, hydrogens, and oxygens are the sand in that container, going back to our initial example. To decrease the mass of the container, you need to take more sand out than you put in. Same basic principle applies to the human body and adipose more specifically. Yes, it is that simple. So in summary, the fuel mass in the form of expendable molecules, CO2 and H2O, need to leave our body, this container called our body, or to be more specific, adipose, than what is being put into our body, or adipose. So with that said, in order to lose body or adipose mass, we need a molecular mass deficit, or a fuel mass deficit. A negative fuel or molecular mass imbalance, if you will. Less mass coming in than going out. So how can we measure how much fuel mass is coming in and how much fuel mass is being expelled in the form of CO2 and H2O? Well, it is relatively easy to know how much fuel mass we put in. We can just look at how many nutrients we consume. How much fat, carbs, and proteins we consume can be fairly easy to determine. You just need to track it. Now, what is difficult is determining how much mass is being expelled from the body. Since mass is expelled from the body in the form of CO2 and H2O, we would need to collect respiratory gases and excretory fluids all day, every day to estimate how much mass is being expelled from the body. Not a very pragmatic approach to figure this out, right? So what variable can we use instead of fuel mass? Calories. Why? Well, a calorie is a measure of energy which is obviously contained in fuel sources like the nutrients we consume, fats, carbs, and proteins, for example. Specifically, a kilocalorie or kcal is a measure of the heat energy required to raise the temperature of 1 kilogram of water by 1 degree Celsius. Remember, when we oxidize fuels, much of that energy is released in the form of heat. So we can use this measure as a way to estimate how much fuel mass and thus energy is coming in and how much energy is expended and thus fuel mass expelled from the body. So caloric or energy intake is used as a proxy measure for how much fuel mass is coming in, and caloric or energy expenditure may be used as a proxy measure for how much fuel mass is being expelled from the body in the form of CO2 and H2O. Since fuel mass balance is the foundation of body mass regulation and calories are an indirect but practical measure of fuel mass, caloric balance, therefore, is the foundation of body mass regulation. There is no mystery or magic behind calories. It is simply a proxy for fuel mass to help us estimate how much mass is going into our body and how much mass is exiting our body. So you can tell this to anyone who refutes the role of calories in body mass control. For example, if someone says you don't need a caloric deficit to lose weight, they are also saying that you don't need to put less fuel mass in than fuel mass going out to lose body mass. If you believe that a caloric deficit is not required for weight loss, then you also must believe that a container full of sand can decrease in mass without any imbalance of sand being put in versus scooped out. Again, it is all about mass, and calories is a proxy for mass, fuel mass to be more specific. So yes, calories is the most important variable in body mass control. Let's dive into this further. We are all somewhat familiar with the energy balance equation or model. Now, just to reiterate, energy and calories are one and the same in the context of our discussion. So when I say energy balance, I also mean caloric balance and vice versa. So the energy balance, as alluded to earlier, is two-sided. On one side, there is total energy expenditure or overall metabolic rate. This represents the total energy needs of the body. This is usually measured as a daily rate, so total daily energy expenditure. And on the other side, there is total daily energy intake and availability. So the fuel that is available in your body and the fuel you are putting into your body. These are your nutrients that are the sources of energy for your body and its cells. So you can see on the left of this balance, total energy expenditure is comprised of three general components. Now, some of these can be further broken down, but let's keep it simple for now. Now, constituting approximately 10% of total energy expenditure is diet-induced thermogenesis, which is the energy that is expended during the process of digestion and absorption. So yes, energy is expended when you consume energy. It is not a one-to-one ratio, however. Obviously, otherwise there would be no net energy available for our cells and we would die. Next, we have TEA, which stands for the thermic effect of activity, which is energy expenditure associated with physical activity, which include exercise and non-exercise activity. Thus, thermic effect of activity can be further broken down to exercise-related thermogenesis and non-exercise activity thermogenesis, or NEAT. Keep in mind as a side note that thermogenesis is synonymous with energy expenditure, since again, as I said before, when energy is released from fuel and expended, much of it is in the form of heat, while the remainder is used to drive cellular processes like muscle contractions. Thermic effect of activity accounts for approximately 30% of total energy expenditure, but can obviously vary depending on how much activity you do. Now, the major component of your overall metabolic rate is resting energy expenditure, also known as basal metabolic rate, or BMR for short. Now, BMR is the energy that is expended to meet the minimum energy required by the body to keep it running. So BMR, or resting energy expenditure, is equivalent to resting or basal energy needs, the minimum amount of energy to keep your body alive. This accounts for about 60% of total energy expenditure / needs, and is a focus of discussion when we talk about adaptations to energy surplus or deficit situations, and why we eventually plateau in body mass when we are in a caloric surplus or deficit for a prolonged period of time. More on this soon. Now, just to reiterate, on the right, which again represents total daily energy intake and availability, is comprised of all the energy containing molecules, aka fuel, aka nutrients, that you consume and store within the body. So this is the total exogenous fuel consumed and endogenous fuel available. Now, below here are three key fundamental points regarding the energy balance model. This is very important for you to understand before moving forward. First, energy balance, or more technically, energy homeostasis, is tightly regulated through a multitude of mechanisms that are interlinked within the body. In other words, your body works really, really hard to maintain this energy homeostasis, keeping the balance flat as shown here. Meaning total energy expenditure and total energy intake and availability are balanced. Why is this important for the body? This is because tipping this balance in either direction or creating an energy imbalance is a stressor to the body. This will in turn induce an immediate or stress response to rebalance it. This is really important to understand. Disrupting energy homeostasis or balance is a stressor to the body. Think about it. When there is, for example, less energy coming in and available than what is needed and thus expended, don't you think this is a situation that is in opposition of survival? The body expending more energy than what is provided and available. Of course, this is unfavorable for survival, since survival is predicated on cells being able to stay alive and energy being required for that to happen. So as you know, anything that challenges survival is a stressor, and your body will immediately respond to deal with that stressor. The same goes for an energy surplus. This does not necessarily challenge survival per se, but the body sees that it is getting more than it needs, and so there's going to be an acute stress response to this situation as well. We will discuss this further in the next few slides. So this third point here relates to what happens if a disruption in energy homeostasis, or in other words, an energy imbalance, is sustained over an extended period of time. What happens when a stress is continuously imposed on the body in general? We know that adaptations to that stressor occur. Yes, your body will eventually undergo adaptations to the stress of energy imbalance, whether it's a positive energy imbalance or a negative energy imbalance. This will happen over time to rebalance the scale and reestablish energy homeostasis. So, if the scale is tipped in any direction for an extended period of time, your body will undergo adaptations to flatten this scale, to rebalance this scale, to reestablish energy homeostasis. What we will discuss further as we progress along is which side of this balance does the acute immediate response to energy balance target to rebalance the scale, and which side of the balance does adaptations to sustain energy imbalance target to rebalance the scale. Again, both acute responses and adaptations are means of reestablishing energy homeostasis. More on this as we progress along.